Born to Learn is a special presentation of KSPS Kids Forward, an initiative on early learning, and made possible thanks to the support of Empire Health Foundation, the Hagen Foundation, Adele and Harry Roberts, and by viewers like you, friends of KSPS.
Have you ever wondered what's going on in there?
There's a bang going on in the brain as input comes in and the brain is forging its connections and building networks.
Scientists now know it's nothing short of rocket science.
What do babies know to begin with? What do they learn from us?
A baby's brain is a work in progress. It is the only organ that is unfinished at birth. Billions of brain cells, called neurons, are waiting to be wired together, to talk to each other, to connect, forming a complex circuitry of neural pathways.
The human brain is not a static organ at all. It is constantly changing. It's very adaptable.
This creative energy that the brain puts to work in a totally novel way during these early years, in ways that you and I don't do later. We're simply not building networks at that rate. It is really a critical period in development.
This time period is the most important in a child's life. It sets up their ability to form strong relationships. It sets up their ability to learn new information. It sets up their potential contribution to our society later on.
A baby's brain is born ready to learn. Its job is to form connections, to wire together the brain's network of neural pathways for processing information.
Brains don't come knowing what the system that the culture uses is going to be. They're just ready to build networks to detect those systems, those languages, those mannerisms, those habits, and those faces and voices.
Babies naturally want to interact. A parent who talks to their child is helping them develop important language connections in the brain.
Human babies, you may have noticed, are not born and then walking out of the delivery room. They can't even roll over. They cannot hold up their head. There's a long period of immaturity in the human species that is really quite striking. And it's been a puzzle for evolutionary biology. Why is this species, human beings that are so smart, why are they born so immature? And it turns out that those two things are tied together. Their immaturity is what allows them to learn much more outside the womb, and that's a really clever trick for eventually ending up with a very, very smart human being.
Nature and nurture are both needed for healthy brain development. It's a complex dance between genes and the environment. Genes are like the seed, the potential, and the child's early experiences are like the soil, the sunlight, and the care that determine how the plant will grow.
The initial targeting is all genetically programmed. Basically to fly from New York to Chicago, that's all pre-programmed. But then getting to the right address and the right street and the right zip code, that final target is what is shaped by experience. There's sort of these choice points of which local address you're going to go to, and that is where a child's experience makes the final decisions.
Although brain development begins before birth and continues throughout adulthood, the most rapid development occurs in the first 3 years of life. By age 3, a child has 3 times more brain activity than an adult. The brain overproduces the number of synaptic connections it will eventually need. It becomes very dense and will remain that way throughout the first decade of life.
Brain development works in a way that these connections keep getting formed and they overproduce themselves. So it's as though the brain is getting ready for everything, and so every neuron tries to connect to every other neuron. So you produce a brain that's got more connections than it really needs. And by the age of 3, they have 3 times the number that you and I have. So the process of the brain is to over-proliferate these connections and then systematically prune the ones you don't use, that you don't need.
Repeated experiences over time determine which circuits stay in service. The pathways used the most will get stronger. The ones less used will be pruned away or eliminated.
And that pruning starts kind of in the year 4, year 5, in different places in the brain at different times. But by puberty, that brain has really been pruned. And so I have parents say, I don't want my baby to prune. I mean, maybe we want to stay unpruned. I say, well, no, you want the baby brain to prune. Pruning, like for a rose bush, will strengthen all the remaining connections. And as you prune systematically, if you do it correctly, you end up with very strong stems. And that's exactly what the brain is accomplishing by pruning the unused connections.
By pruning, the brain becomes custom designed to function in its own environment. The developing brain is very flexible, or what neuroscientists call plastic.
And the human brain is not a static organ at all. It is constantly changing. It's very adaptable. It's like the smartest of the smartphones that can learn from what you typed before and know what to enter next time. So those circuits are not fixed or hardwired from birth. They are evolving, they are developing on the fly based on the experience that's happened up to that moment.
This plasticity enables a developing brain to be open to rapid learning. This flexibility also makes the developing brain very vulnerable to both positive and negative experiences.
There's this kind of window of opportunity during early childhood to have a positive influence on kids' later trajectory. It also tells us that that can be a really vulnerable time for children and that we really need to pay attention to what's happening during that time.
Located in Seattle is the University of Washington's Institute for Learning and Brain Sciences, called iLabs. Its co-directors, Dr. Patricia Kuhl and Dr. Andrew Meltzoff, are two internationally renowned scientists known for their research in early brain development.
Well, the striking thing about babies is not only that they know more than we thought they knew, and they knew it earlier, but that they learn so rapidly and more flexibly than we adults do. And one of the things that intrigues us here at iLabs is, why is the brain so open to learning?
Dr. Patricia Kuhl is considered one of the world's leading authorities on early language and brain development. She calls babies universal citizens of the world and computational geniuses.
At birth, no matter where you are testing a baby, no matter what language the sounds come from, babies across the planet can hear all these very small differences between the sounds that distinguish words. And you and I, as adults, no longer can do that. Our brains have been shaped by the language experience we had during the first 7 years of life. And so the babies are citizens of the world. They can do it all. They're ready for any language. But you and I are now culture-bound listeners. So whatever language or languages we were communicating with in the first few years are the ones that our brains have honed their networks to detect.
So how long are babies universal citizens of the world? Not for long. Before they reach their first birthday, a baby is already becoming a culture-bound listener. Their brain is selectively wiring only the sounds they need for their native language. Language has a critical period for learning. During the first 7 years of life, babies and young children are exceptionally good at learning language. Once they turn 7, their ability starts to decline. After puberty, it falls off the map. iLabs is trying to figure out why it works this way. Why is there a window of opportunity for learning language that opens up and then closes? Is there a way to make it stay open longer, or maybe never close at all? At iLabs, Dr. Kuhl works with babies who are trying to learn which sounds are used in their culture's language. Kuhl says babies come with surprising learning mechanisms. One is computational, and the other is social.
From a computational standpoint, babies they look like geniuses because they're sensitive to the statistics of the impressions their senses get. So in the world of language, they're sensitive to how frequently the sounds in their language are coming through as people talk to them. So if you're listening to speakers of English, there are lots of R's and L's.
I love your big blue eyes, so pretty and so nice.
If you're listening to speakers of Japanese, there's hardly any R's and L's, but the intermediate sound, Japanese R, is very frequent.
うわは大きくて可愛いお目目すごく青くて綺麗ね
So the baby brain, before the brain recognizes any words, recognizes the frequency of sounds. And the frequency of sounds changes their brains, creating this more dedicated listener.
Babies also put their social brains to work.
望着月亮，还跟妈妈说：“哎，妈妈。”
Kuhl says babies only take statistics when they're interacting with a live human being.
We know this because we did experiments in which we exposed babies here in Seattle to either Mandarin or Spanish at 9 months of age for the very first time. And what we saw is that they learned phenomenally from 12 sessions of just playing on the floor, hearing a native speaker. They learned the sounds of those languages. They could distinguish them perfectly well at a time when their brains would have normally now not discriminated those sounds. So what we showed is that in the presence of a live human being talking to you, the babies learned so well they were indistinguishable at 11 months from babies in Spain or babies in Taiwan.
A la luna.
Would watching a person on TV do the same thing?
Those babies learned nothing. Even though they stared at the television set, they learned absolutely nothing. So there's something about social interaction and the presence of another human being, live human being, that creates this opportunity to put the computational genius to work. But you and I, going to France or going to Japan, can hang out for a month and attempt with all our mights to learn, and the statistics of those languages are not being picked up by our brains, not anymore, because our networks are fully formed, dedicated to analyzing the exact signals that we were exposed to early, and only those signals. So in developing that expertise, we've lost some of that sheer openness that the baby brain comes with, and that ability to learn what's in front of you no matter what.
In 2010, iLabs opened its MEG Brain Imaging Center.
It's a first-in-the-world brain imaging device that allows us for the first time to look under the hood, as it were, to look at babies' brains as they touch somebody else, as they hear voices, as they hear language.
MEG lets scientists see a child's brain in action, how it grows, how it acts, and how it reacts.
I think one of the most exciting things is to actually witness a brain image of a child, because from the moment you could begin to really see, and not just a snapshot, but a movie of what goes on as a child hears a word, is simply amazing.
The images show how interconnected the brain really is. When a baby hears a syllable, it lights up the auditory area of the brain as expected, but surprisingly, it also lights up the motor area.
Now, the motor area of the brain is what babies use to talk back. And these are only 7-monthers. A 7-monther has typically not even started babbling yet. No ba 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 ba. No early word formation. We interpret it to mean that babies as early as 7 months are beginning to rehearse. What does it take to do that myself? They want to join this social conversation. They're so socially driven that the sound of speech makes them want to do similar kinds of things. That's what people in this culture do. I want to do that too.
Two little ladybugs basking in the sun. Along came a frog. Ribbit, ribbit. And
Talking to babies, singing and rhyming about anything and everything. teaches them about language. These interactions help build language skills long before a child can talk or understand what's being said.
Kangaroo.
Babies particularly love to listen to what experts call parentese.
It's a signal that has an acoustic signature that's really unique. If I happen to have a 2-monther on my lap and I suddenly stop talking to you and turn to the 2-monther, I would say something like, "Hello, how are you? Let's open those big blue eyes." And so you're animated, and your face and your voice and these pitch contours are wildly gyrating in a way that babies love. And it's slowed down, so actually when you analyze the sounds, your speech is clearer.
Does talking parentese to your baby improve language development? iLabs wanted to find out. One study recorded what babies were hearing at home.
So what the recordings have shown us is that kids whose households have a lot of parentese going on, and especially one-on-one interactions, have not only at that time, there's more babbling going on by the baby, but their language development at the age of 2 is greatly enhanced. So in the high prevalence parentese one-on-one families, as opposed to the low prevalence parentese one-on-one interaction families, the babies are producing 433 words on average at the age of 2, as opposed to 163. This is not a small effect. So parentese makes a huge difference to language outcomes.
For decades, iLab's co-director, Dr. Andrew Meltzoff, has studied newborn babies during their first hours of life.
We're right there at the beginning. We're at the big bang, right when the brain development is taking off.
Meltzoff observed that a newborn will imitate another human being. It's one way they learn.
We were able to show babies very, very simple gestures, such as putting out your tongue or opening and closing your lips. We demonstrated that babies were able to imitate the gestures of other human beings. And what's so amazing, astonishing, and important about that is it means that a baby at birth recognizes that you are like me. Imitation is a key mechanism by which babies, before they have language, can learn about all the interesting things in the world.
Imitation is one reason caregivers are a baby's favorite plaything.
Children are learning like sponges, and they're learning from you. They're learning from the adults around them. Babies are not born knowing what a telephone is, but they see other human beings holding telephones to the ears, walking around and talking mysteriously into empty space when there's no one there. It must be a very curious sight for little babies. But sure enough, one of their favorite things is a toy telephone because they see other people using it. It's imitation.
Meltzoff says babies are like little scientists, conducting cause and effect experiments.
When they drop a spoon off the high chair, in fact, they're trying to drop it off and see if it hits the ground again. It hits the ground on the right side when I drop it, on the left side when I drop it. It never goes up. It always falls in a straight line down below where I drop it. That's something babies need to learn, and they are doing those cause and effect experiments at home in the high chair, probably in the restaurants when you're trying to stop them from dropping the spoon off the table. They're doing little experiments about gravity, and you're interrupting their experiment.
In a new study, Meltzoff is using the MEG brain imaging technology to examine how the sense of touch lights up a child's brain.
In a human being, if your foot is stimulated, a part of your brain here lights up. And if your hand is stimulated, if somebody touches in your hand, then a little bit laterally off to the side, there's a hand area in the adult. And there have been exquisite mappings of the adult brain to know whether your hand is and where your foot is and where your wrist is and where your lips are in the brain. There's a little body representation in the brain. But no one knows about the body maps of infants. What we are discovering is that when the mother holds the baby's hand, it's lighting up a particular region of her brain because her hand is being stimulated, but it's lighting up the parallel same place in the baby's brain. So you can imagine when you're touching the baby's hand, you're touching their brain, you're stimulating their brain. And when a mother and baby holds hands, the same part of their brain is lit up and pulsing together. And we think of this as this primitive sense of touch as a foundation for other social emotional development.
Is there really right and left brain thinking? New brain science is showing how interwoven our brain really is.
We used to think they were on separate sides of the brain or something, as though left hemisphere is doing all the official stuff, you know, the language and logic and math and judgment and all of this hardcore stuff. And the right side of the brain is soft and fuzzy and it's doing music and it's doing social and love, etc. That idea that these are completely separate areas of the brain and that, you know, you can work on one or you can work on another, or you can be a genius at one or a genius at another, but that they don't unite is really nonsense. The new brain work is showing how tied your emotional outlook is to every piece of learning. So if language, which is the ultimate computational phenomenon that goes on in early childhood, requires a social context, requires social interaction, that just upsets the apple cart. It's that the whole brain is involved in everything we do, and that the social parts of our brain and the more logic, linguistic parts of our brain are totally interwoven.
Are bilingual kids smarter, more creative? Does learning a second language make the brain more open to learning later in life?
The bilingual brain is different. We're just learning how different it is. The bilingual brain looks as though it's got more connections. It's connected in a way that where more creative pathways have been forged probably by necessity, as the brain is trying to learn the contexts in which language 1 and language 2 occur. What we see are two things that make the bilingual brain perhaps having some advantages. The first advantage is they seem to learn over a longer period of time. It's as though the critical period opens a little bit wider. So instead of it being a narrow window opening for sound learning, it seems to be a little broader in bilinguals. And then secondly, they're more creative in problem solving. So it's a cognitive skill that doesn't make them smarter, but makes them more creative if they have to solve a new problem.
When a baby is born, its brain is a quarter of the size of an adult brain. On the outside, it looks like a smaller version of an adult brain.
But if you look under the microscope, it's a very different beast. At the cellular level, we see that the neurons in the cerebral cortex of a newborn baby are very small and not well connected.
The neurons of a newborn look a lot like young tree saplings, standing unconnected, with short branches and a stubby root system.
In a forest of these saplings, they're not connected to each other, but by the time they grow up, the branches reach out and touch their neighbors, so you have this whole forest canopy that thickens.
The structure of a neuron is much like a tree. Its branches, the dendrites, surround the cell body, receiving incoming electrical signals from other neurons. The root, or axon, is a long cable extending from the cell body, transmitting electrical signals to other neurons. A synapse occurs when the axon of one neuron connects with the dendrite of another. The dendrites grow very rapidly in early development, causing the brain to grow.
In fact, that's the main reason babies' brains get bigger. They're not adding new neurons, but they are massively growing these dendrites, so your dendritic branch is growing.
By age 3, the brain will have grown to 80% of its adult size. By age 5, it will be 90% of its adult size. Brain cells are unique. Unlike other cells in the body, most brain cells cannot reproduce themselves.
Probably the most remarkable fact about brain development is that we produce all of those 100 billion neurons in just the first 2 months of prenatal life. So already by 6 months of age, a baby has all the neurons they're going to have.
And they look different than other cells.
The brain cells are quite different. They are long and spindly. There are neurons in your spinal cord that extend all the way down to your big toe, so they can be, a meter long. So the actual cell body, where the nucleus and the DNA is just a tiny little blip on this enormous long cable.
To help insulate the brain's electrical circuitry and speed up transmission, the neurons need a fatty substance called myelin.
Myelin is the white matter of the brain. It is largely not present in newborn babies' brains. It's added after birth. It's one reason we like infants to stay on a higher fat diet. The myelin literally wraps around this long cable of an axon. It insulates axons, our neural wires. And so if you have 2 axons running alongside each other, the fact that they're insulated with myelin prevents them from interfering with each other.
Myelination begins around the time of birth in the cerebral cortex, but it continues all the way into our mid-20s.
Myelin is a marker of maturity. So once a brain area is fully myelinated, it probably loses some of its malleability or plasticity. Once the cables are all wrapped up, it's much harder for them to branch out and form new connections.
Recent research indicates that myelination may also be affected by experience.
So one of my favorite studies looks at a bunch of teenagers who are learning how to play piano.
The more the teenagers practiced the piano, the thicker their myelin became.
You will actually have thicker myelin connecting your 2 hemispheres. Probably everything we're doing is, in addition to selecting the right synapses, it's probably also increasing the thickness of myelination.
Dr. Lise Elliott is a neuroscientist at the Chicago Medical School of Rosalind Franklin University. She is studying neuroplasticity, a neuroscientist's word for describing the malleability or flexibility of a child's brain.
Just like plastic, you can turn into grocery bags and playground equipment, and our brains have tremendous ability to develop different circuits depending on the needs of the child in their early environments.
A young brain is more plastic or open to rapid learning and growth. So what's actually happening inside the brain? Elliott says the dendrites are at the heart of plasticity.
That's where experience is making the decisions. We've got a little branch growing along. Am I going to go right? Am I going to go left? Well, if something over here to the right is a circuit that's useful to you, like knowing the sounds of the English language, then the branch is going to grow and grow in that direction and solidify that circuit. If the alternative direction for the branch to grow is a sound in Hindi or Chinese, then the branch won't grow in that direction. So it's this massive growth of the branches that completes the wiring and sets down the circuits that we will use for the rest of our lives.
When it comes to wiring the brain, timing is also an important factor. Certain things need to happen at certain times. Scientists now know that starting before birth, waves of important critical periods or stages of development need certain types of experiences in order to wire up properly. These windows of opportunities open and shut at different times very early in a child's life. Surprisingly, even a baby's vision is not hardwired at birth.
If there's anything people might expect would be hardwired, it would be the sense of vision. Why not just open our eyes and have these camera images perfectly projected into the occipital lobe? But it doesn't work that way. Even vision depends on early experience. And so that's why we're very cautious with children who have any kind of visual problem. If a child has a weak eye, a crossed eye, we call strabismus, they tend to squint that eye. And when you squint your eye, you deprive your brain of vision. And when your brain is deprived of that electrical activity from the visual circuit, it literally cuts off the input. It literally loses connection to the eye. And if that problem is untreated in a child for the first year or so of life, they can end up functionally blind in the eye. The eye may look fine, but the brain isn't getting the connection. And this is very different from what happens in an adult.
An adult would not have this problem. If they develop a vision problem, once it was fixed, they would see normally again.
Your vision will go back to being what it was before. It doesn't have that unique sensitivity to the experience that a newborn baby's brain does.
Critical periods come with time limits. If the right kind of experiences don't happen at the right time, then essentially a child's brain will be operating with a handicap, struggling to make up lost ground. So, how do we build a healthy brain? Brain building is a step-by-step process. Simple neural pathways form first, and then more complex ones. Just like building a house needs a strong foundation, the developing brain needs a strong base to build all future learning.
If your foundation is not solid, you could have a really pretty house that's going to fall down in a windstorm or, be cast aside. You've got to have that solid foundation.
The kind of care a child receives plays a big role in how the brain chooses to build itself.
Every interaction with a young child is a brain-building opportunity. There's nothing that's neutral. Everything is either supporting that child's development and saying, yes, you can, or saying no. And so every interaction counts big time.
You are. Good job, Dustin.
Experiences in the first years of life build either a strong or weak foundation for all future development. It determines whether a child gets a strong or worrisome start in life. So how does the brain build a strong foundation? One way is through serve and return interactions. Similar to a tennis match where a ball is hit back and forth, a caregiver and a child send various forms of communication. It could be a smile, a touch, a word, or a coo.
Every interaction, as people talk about, is serve and return. It is a rhythm, a dance, a synchronicity between the caregiver and the child. And every interaction builds the child's skills and willingness to move forward.
Children really, really need another nurturing human being to interact with. But it's not just having the FaceTime, it's having a caregiver who is noticing what the child is interested in, noticing what their needs are, and responding to those interests and those needs and desires. And it's this kind of back and forth interaction, just like a game of tennis, just like the serve and return. It's that type of interaction that really teaches children about emotions, teaches children about social interactions, teaches children about language, and gives them the kind of foundation that they need for everything that comes after.
In many ways, we come into this world wired for that interaction. And interactions really do form the basis of brain development. Every time there is a serve and return interaction, children are picking something up from that. Every time a parent or a teacher helps a child name something that they're interested in, for instance, there's a process in the brain that's learning language through that interaction. And children learn best when they're able to feel a sense of safety and security within a relationship that helps them explore outward and not have to worry about those kind of primitive safety issues. And all of those interactions are helping form those tracks in the brain.
Every interaction really, truly shapes not just the child's school readiness, but it shapes their adult life, their adult health. It is just phenomenally impactful.
So what happens to the brain if a child does not get healthy serve and return interactions?
It's kind of a double whammy, because then if they don't have those serve and return interactions, those healthy responsive interactions with their caregivers, then they're not only missing the kind of healthy input that they need to develop, but it can actually ignite their stress response system because what they're expecting to get isn't happening.
Stress is another kind of experience that shapes brain development. There are good kinds of stress, like trying something new or taking a test. And bad stress, or what experts call toxic stress, that damages brain development. Toxic stress is when a child suffers from serious ongoing hardships, neglect, or abuse.
When they're in an environment that's overwhelmed with stress, we know that that shapes the brain in very particular ways. You can end up with all kinds of problems in learning, in behavior, in your ability to function in relationships with other people as a result of that very early wiring that's impacted by toxic stress.
Toxic stress is, as it sounds, it is constant, it is unrelenting, it is there all the time. It affects the function of the brain. Because what stress does is it raises your activation syndrome, it's called. When you see a tiger, you either freeze or run, fight or flight. And a little bit of that, okay, conditions your system. But imagine you're a child growing up and it's always that way. You're always stressed. I mean, it doesn't go away. You never have a chance to, relax, to breathe, because you're always on lookout. Children under those kind of circumstances either are overly afraid, overly frightful, or nothing bothers them because they're overwhelmed. They're overloaded, and neither thing is good.
We've learned that entering school ready for learning is critical, that kindergarten readiness idea. But we also know that it's not just being academically ready, it's not just the language skills or math skills that they come into school with. It is that social emotional readiness. Children who are experiencing a great deal of stress are emotionally aroused, and we know that blocks learning from happening. And if they don't have the social skills, the capacity to sit still, to regulate themselves, to participate in the classroom in an effective way, to pay attention and focus their attention. So those are, self-regulation and social skills that we might overlook when we think of academic readiness or academic competence or educational attainment, but those are the foundation of those things. If a child's sitting in a classroom and they're stressed and they're emotionally distressed, their mind's on something else that's going on, they're unable to sit still, they're unable to pay attention, learning can't happen.
And thinking about toxic stress in early childhood has kind of given us a new lens at the way that we view what children need. So not only do they need enriching opportunities to learn in the settings that they're in, but they also need protection from sources of toxic stress.
A strong brain foundation also supports the development of emotional and social skills.
How do I learn to not just blurt out what I want or grab something that I want or push my way? I'm civilized in that I wait my turn, I breathe before I act, and it is part of a civilized society.
So we are going to play a game with these cards. It's going to be a silly game. When you see this card, I want you to say the word day. Can you say the word day?
Day.
Good job. And when you see this card, I want you to say the word night. Can you say the word night?
Night.
Great job.
Skills like executive function and self-control are important for a child to develop to do well in school and life.
Executive function skills are the kinds of skills that help us focus our attention, to switch between different kinds of tasks, monitor our behavior, to self-regulate. And so those skills are really important.
Executive function in the brain works a lot like a control tower at a busy airport. The control tower, or young brain, needs to manage numerous planes landing and taking off. To avoid a crash, the child must learn to pay attention, plan ahead, and follow a lot of rules.
If you are not able to attend to information well because you're distracted, or you can't control your impulses, or you can't recall the steps of a sequence of something you might learn or be asked to do in a classroom setting, you're not going to be successful with learning. So it's really those foundational pieces that help us learn new information. And without those in place, it's very hard for us to take new information in.
Executive function also helps a child get along with others.
So much of our world is about being in relationship with other. And so children who have poor executive function skills have difficulty in friendships, have difficulty in peer learning situations, because they are not able to take the cues of others well and organize their behavior in a way that's sort of pro-social. So executive function is really important for both that cognitive development as well as the social development of children.
The rule of the game is no peeking. Try not to look.
Children are not born with executive function. It needs to be learned from their caregivers.
Executive function is one of those things that we have the capacity to develop. And in children, they're working really hard at building executive function. And it starts, right at the moment that a child is interacting with another person. So really in infancy, those responses that are, those sort of, we call them serve and return, those back and forth interactions really set the stage for executive function development. And then we see a huge spike after children learn language in the preschool age group between 3 to 5. And any teacher who works with 3 to 5-year-olds will say, you see those kids working on things like impulse control and being able to transition and shift activities seamlessly. Those are things that kids are really actively working at. And then it continues to develop throughout life. It's one of the areas of the brain that develops the latest. And so we see another spike in development in early adolescence into early adulthood.
At Whitman College in Walla Walla, Washington, Dr. Melissa Clearfield studies babies. She's interested in the achievement gap between low and high-income children.
We know from about preschool all the way up through high school and college that low-income children don't perform as well academically in nearly every way that we can possibly think to test them. And my question is, when does that start? Because I don't think kids show up to preschool equal and then it starts going downhill in preschool. So I'm an expert in infant development and infant cognition during the first year of life. I wanted to see if we could start seeing the beginnings of differences during the first year.
One difference Clearfield found was in executive function.
In infants, that means things like attention, cognitive flexibility, so the ability to shift your attention from one thing to another, and early problem solving. And what I have found is differences in all of those areas by 6 months of age. What surprised me was how robust those differences were, how little they changed from 6 to 12 months. I didn't start out looking at executive function. It's just those were the tasks altogether where I found the strongest delays and deficits.
One task looked at attention behavior.
What we're looking for there is how long can infants stay looking at the toy while touching it, actively engaged in it. What other studies have found is that how long infants spend actively focusing on that toy actually correlates to their attention behavior at age 3, 5, 7 years. It's related to diagnoses of ADHD at age 5 and 7. So you can really tell a lot by how much time infants spend focusing on one toy.
Clearfield also tested a baby's selective exploration skills.
When I hand an infant a rattle, and the infant picks up the rattle and turns it over in her hand and looks at it from different angles and bangs it on the table to make noise, and then picks it up and shakes it, that infant is selectively exploring. She's gaining information about the weight of the object, about how it looks from different angles, about how it feels when you hit it against a surface, about the noise that's produced when you do that. All of that information is active and purposeful.
The information Clearfield has gathered is disturbing.
There are differences, even by 6 months, in how infants attend to objects, how they interact with them, and then how they use that information to solve problems. And so this suggests that whatever different brain development trajectory that we see in older children, it is starting before 6 months. Since most interventions begin in Head Start or even early Head Start, which is usually starting around age 3, we're really missing prime opportunities to intervene for these at-risk infants.
Hey, good job.
What I suspect is that being a little bit behind now will just contribute to this overall pattern of being a little bit behind at age 2, at age 3, at age 5, a little bit behind in readiness to learn when starting kindergarten, and that contributes to that overall achievement gap that we see all the way through school.
Jason Gortney spent years working with troubled teens.
I just saw so many kids who were struggling with so many issues, behavioral challenges and mental health issues and just emotional regulation issues, and just suffering a tremendous amount of pain, having difficulty trusting.
Gortney soon saw a pattern. The one thing all the teens had in common was a traumatic early childhood.
It was only in the last 10 or 15 years that we really became aware that, in fact, trauma in early childhood shapes the brain. It shapes the way that the nervous system develops, and it interferes with the development of some of those key areas of the brain around being able to regulate emotions, being able to engage in healthy relationships with other people. All the kinds of problems that we were seeing in the kids that we were trying to help. And so we got really interested as that research started to emerge about, okay, how does that happen and what can we do about that?
Gortney decided he wanted to work on the solution. So he began to focus on early childhood.
I became very passionate about the idea that, you know what, all of this should be preventable. Why treat symptoms if we could figure out a way to get to the source and prevent the problem in the first place?
Gortney teamed up with Dr. Holly Schindler from the University of Washington to test potential interventions for at-risk families. One program standout is called FIND, which stands for Filming Interactions to Nurture Development.
What FIND is all about is using parents' strengths and building on those strengths in order to encourage more responsive and frequent serve and return interactions between a caregiver and a child. And I love this program because it really is based on skills that the parent already has and building upon those skills.
Using videos taken of parents interacting with their children, FIND coaches highlight their positive serve and return behavior. FIND has helped many parents like Elise Hagley. Elise is a single mom who had a rough start as a parent.
I'm a woman who has overcome significant obstacles to be where I'm at today. My life has touched the juvenile justice system, the criminal justice system, suffered from unhealthy lifestyle of using drugs and trying to really numb out the feelings of worthlessness that I just did not think I was a worthy human being, and my actions really lined up for that. So I spent years just in a really dark place, and right before my daughter's birth was the worst I've ever been. And when I gave birth to my daughter, I was facing a 7-year prison sentence for the crimes I committed to fuel my addiction. And so right when I gave birth, my daughter was immediately removed from my care and placed into foster care. How many carrots do you want?
Elise worked hard changing her life. But by the time she got her daughter out of foster care, she was already 17 months old. Elise found she needed help learning how to parent.
And I need some positive people in my corner, and that's what FIND does. And it does it in such a loving way that I'm really likely to hear the message, right? You can point out to somebody all the things that they're doing wrong, but FIND completely removes all that out of it and instead visually shows you and has somebody talking you through, look, Elise, when you did this, and you saw your daughter's response, like that's what we want, right? Right now, her brain is so happy, and she's going to be able to build on other stuff.
Today, Elise and her daughter are doing very well.
But what's dramatically happened since I've completed FIND is our relationship has just dramatically improved. You know, I just had our parent-teacher conference, and from being told that she was never going to talk to being a child who does not stop talking. But beyond that, I get to spend every single night with her in my arms, you know.
The more we learn about the developing brain, the more urgent early learning seems.
We're trying to combine the science of learning and scientific discoveries with the practice of learning, and how we can get this information out to people who work with babies and children every day.
In Olympia, Washington, Juliette Morrison oversees the Department of Early Learning's Early Achievers program. Early Achievers is a training program for early learning professionals.
The whole focus of Early Achievers is quality. And it's built to really address some of the challenges in our current system. Yes, it's true that our early learning professionals are not compensated in the way that they should be for this critical work that they're doing. And so Early Achievers is a mechanism to help boost quality in an under-resourced environment.
One goal is to take what we've learned from brain science and apply it.
We provide data in a very objective way and then use our coaching to help programs understand that data and apply new techniques and new ideas to help them think about continuous quality improvement, and that providers will know how to better support children to get ready for school.
The early years really do last a lifetime. Brain science is changing the conversation about the importance of early learning.
You know, I think that the science has really brought a credibility to the birth to 5 space, that this isn't work that, is something that's optional. This is really the place where learning is most rapid. When you look at brain imaging, when you look at when children are making the most number of brain connections, it's in this birth to 5 space. And so I think the science has changed the conversation about the importance of early learning.
I mean, we need to get these ideas into the groundwater. We need to absorb the information that babies have this kind of potential, and that we don't want to waste this child's potential.
That is how we're going to transform education to connect early learning from the moment of birth, even prenatally. When these newborns are opening their eyes for the first time, looking out at us, hungry for knowledge, hungry to absorb our touch, our cuddles, keeping that passion for learning alive during the K through 12 period.
The science gives us the opportunity to think about our developing early learning system and embed that strong research into the work that we do every day, because we know that not only is it critical, but we're also starting to learn impacts later on in life if those things don't happen early on.
To purchase a DVD or watch this program online, visit ksps.org/born to learn or call us at 1-800-735-2377. Born to Learn is a special presentation of KSPS Kids Forward, an initiative on early learning, and made possible thanks to the support of Empire Health Foundation, the Hagen Foundation, Adele and Harry Roberts, and by viewers like you, friends of KSPS.